happy to be the first one to be torn to pieces. See how far we've gotten with this narrative. Some of it may still be a little bit, looking like. Of course, there will be some bias to work package 4, which is actually focused on the genomic tools, because this is sort of a view and a narrative of how the genomic tools can help improving stuff for breeding and management tools. So I tried to reach back a little bit into some of the objectives of GenTORE and try to write it down as in a sentence here that can be improved upon for sure. But in GenTORE, we aim to contribute to diversity-based breeding with diversity for efficiency and resilience, in which adaptation to breeds to local conditions are considered, and hopefully add to the richness of the future possibilities in breeding and management. And with the diversity-rich breeding, we mean in part that this is not just for a specific solution for one of the major breeds like Holstein or others. We like to see some of the smaller breeds come into place. We think that the crossbreeding is in a way that it can but these smaller breeds get a huge relevance in terms of how you can combine capabilities from breeds to target the needs of specific environments. And they're also shown to be sort of efficient and resilient in their own right, and so forth. So we have thought. I wonder how this is working. Okay, so generally 4 different ways we've been working with trying to add genomic information into tools that will help us in this way. And we have been working with genomic prediction across multiple environments. We have been working with different crossbreeding systems and statistical genomic models for allowing us to make selections in different types of animals in crossbreeding systems, and at mixed and multi-population systems. We are working more specifically with genomics of efficiency and resiliency traits. So really more going into the genomic selection for these specific traits, and also building some of these things into management decision tools. So what we have done in terms of genomic prediction across multiple traits, DLO has led the development of a protocol where the multi-environment models, and there are sort of 2 categories, either classical categorical 2 different environments, or more like a continuous gradient. And the novelty in the method here is that it allows for a specific or differences in variances and covariances of SNPs across these environments. So this is a protocol that uses just normal software procedures that are available, but a protocol how to use this. We want to apply this to some real systems, and we'll see a little bit on an IRIS system and a FLECFI, and also in France we have some analysis. In the IRIS system, it was tested. Of course, in the simulations, they saw a slight improvement by using this method. They applied it to a larger, an IRIS situation with 13 breeds, 50,000 animals, and HD genotypes. The efficiency trace was age at slaughter, and the environmental descriptors was contemporary group effects. So the conclusion was that, this was superior to non-genomic models, but they didn't really see the improvement of the heterogeneous SNP covariance compared to a normal T by E model. But we don't give up. We want to apply it also on other systems. So far, what we have done here in FlexFi was try to use some of the environmental descriptors in a previous work package, and that work to sort of categorize which animals were in which groups, and use that as the environmental factors in G/E models. So far in the state-of-the-art models, but after that we will try to use it with the SNP heterogeneity models developed. Going into crossbreeding, well, we believe that, when we met in Padua, there was a big belief that crossbreeding somehow is gaining popularity, and for some good reasons. You can exploit the complementarities of the different breeds. There's the heterosis effects, and we see it as a contributor to this efficiency also on the system level. Here's a small example of how it's employed in Denmark, where there's a combination of dairy crosses that may be a rotational dairy cross, and when you don't need a replacement heifer anymore, you use a bull semen, sexed bull semen from a beef breed. So the thing is that for this, or for especially maybe for even more complex mixed systems, we don't really have the proper methodology, and this is what we want to have worked a lot with in GenTORE. So EMRA has developed this sort of multi-breed model, and you can have any kind of purebreds, crossbreds combined, and we use the phenotypes from any kind of animal. We can get a genomic value for any kind of animal in this system. A novelty is also that so you need first of all to know where all the SNPs, for each SNP in a particular animal, you need to know which breed it originated from in order to specify this model. So there's a few more steps that you need to work with. There's two versions of the model. One where we assume that the SNP effects from a particular breed are uncorrelated from the other breeds, and one where we assume that they are correlated. And that has a big effect on how it works in real data. Here's a short one-page result from a simulation study where it was tested in a rotational crossbreeding. We used real genotypes from Holstein Reds and Jerseys to start the rotational cross. If we go quickly through it, you will just see that the green bars are if we only use a single breed as a reference. Orange, pink is when we combine these breeds, and the blue ones is when we combine all the breeds and use these novel Boer models. So for these crossbred animals in the simulations, there'll be a huge difference, huge increase in accuracy. Even for smaller breeds in the combined analysis, you get a nice increase in accuracy by combining all the data from all the breeds and using these Boer models. So it has the potential to improve selection, both for purebreds and crossbreds, as these systems sort of become more popular.
Mogens, you have a question from Hank.
I'm sorry, Hank. Yeah, go ahead. Are you muted, Hank? Hank, we don't hear you.
Sorry for that, I was muted. What do you mean by accuracy? Because that's the output of the simulation model, I guess. But what's that?
So yeah. I mean, here the accuracy is really just measured by the correlation between the genomic value of these groups of animals and the true breeding value in the simulation.
Okay, that's accuracy. Okay, I thought simulating went way further than this, but that's just okay, yeah.
That's the part we are mainly interested in this particular so it's not a simulation to simulate the breeding scheme, it's a simulation to evaluate this software.
But thank you, that clarifies.
Perfect. Well, one thing is simulation, another thing is real data and real scenarios. And so we're working with a few of those to get closer to the impact, obviously. We started out probably with the most difficult situation, is the Nordic red, which is immensely admixed from different red populations in Denmark, Sweden, Finland, Norway, but also some old contributions from Holstein, from Swiss. And Anna made the test on this model. Unfortunately and disappointingly, of course, we didn't see the improvement that we expected, but we found that the reason for that is that it was the data was not, the genomic data was not clear enough to estimate accurately the breed of origin of the alleles. And it was, we confirmed by simulation that this would have this effect on the accuracies. But it could reach sort of the same accuracy, but no improvement this case, but we know why. So we have something to work with. The second stage here is a even much bigger data set with the 5 breeds in the Irish breeds, 300,000 genotypes, millions of phenotypes, and pedigree animals. And here it's a relatively more clear crossbreeding system, and we do see a significant improvement for the crossbred animals. And we are testing similar models in rotational crossbreeding system, ProCross, between Holstein, Nordic Red, and the Mulbeyard. So of course, we have been concerned about, how do we bring all this value to industry? And one issue with the basic model is that it's computational, very heavy. So we're working with 2 ways to make it into scale applicable. One way is to make sort of a blending model where we use summary statistics from the big populations, purebred populations, and phenotypes from the crossbred animals. So it's very relevant if you have many purebreds compared to crossbreds, but also relevant if you can get SNP solutions from a different country, but not the phenotypes. We're also working to build this into a single-step blob breed of origin model, which can handle, millions of individuals in principle. And in terms of implementation, we are working with these 3 cases. We are working directly with some of the evaluation centers, and we're trying to pitch some of these novelties in the summer school close to the World Congress. All right, so we're also working, as I said, directly with the efficiency and resilience traits. Here's the case for dairy feed efficiency or residual feed intake models. And we are working, the work with this model, as Nick said, is going across the work packages. So it started as more of the phenotypic model in work package 2, and it's now becoming a genomic model. Well, you probably know this kind of formulation for these residual feed intake models, and we're working with data from several partners and also international consortia. There was also a lot of discussion on the models for resilience, and in the genomic work package, it ends up to be sort of improvement of accuracy of prediction for length of productive life. Is something that the French have worked a lot with, and it can include many different sort of information traits, and they may be different from different countries. It's a 2-step procedure where you first analyze the individual traits with the best model for those traits, and then in the second step, combine adjusted phenotypes from those analyses into a multi-trait single-step analysis. And I think it will, or it's not probably not yet, but it probably will be implemented in France. There's also the work package with the management decision tools, work package 5, and here where the genomics also comes into these indices, and they're working with different breeding indexes, sire-bias, production culling indexes, and animal value indexes. Just one example here. So So this is sort of the a way to analyze at the current state of each animal, taking into account the genetics, heterosis, permanent environmental effects, the states of where the animals are, and always predict the future worth of each animal such that you can rank them and make the informed decisions about which ones to cull, which ones to breed, which ones to handle in different ways. So this was my attempt of a quick overview. Maybe I'll just stop there.